On the HYDRAN-XR website, there are example files that you can download. So when you download that file, it will create a folder called testing, and that testing folder has subfolders. And in the previous video, we worked through the examples subfolder, and that contains examples of rigid body hydrodynamics, single, two-body, and three-body problems. But we're unconnected. It was just strictly connected, if you will, through the fluid. So it was a fluid structure problem. When we were doing multi-bodies, another one, there was also the single body example. In this case, we're going to go through the examples in the MOB RMFC folder. This one here, MOB is Mobile Offshore Base, and RMFC stands for Rigid Module Flexible Connector Model. Let me pull up a slide that shows what I'm talking about the Mobile Offshore Base. This is a slide from the lectures on linear hydroelasticity, which are available from the website and the videos. And this is a schematic that shows a 5-module MOB. Each module is a semisubmersible, and they are connected at the deck level. And so we're going to be looking at how to model this structure in HYDRAN. So if we open up this file, so we have, it's probably a good idea to read the README file. I will let you do that. But let me also pull up a couple of papers. So this paper is from the Journal of Ship Research, and it discusses the response characteristics of serially connected semisubmersibles. In other words, serially or linearly connected, connected semisubmersibles. So this is the discusses the problem that we're going to be talking about today. And there's another paper here. Let me pull up. And this one is, again, it's a multi-module mobile offshore base, and it also discusses essentially the same problem that we're talking about today. They have different foci, these two papers, but you may want to reference them if you have certain questions. All right, let's come back to here. So there are a lot of files here, and most of them are associated with different ways of modeling the connectors. We'll get to that in a minute, but first, the file we need to run is mob.txt, and what this file does is it just generates the added mass, hydrodynamic damping, and wave exciting forces for the 5-module MOB. Now, those quantities are independent of the connection of the modules, so that we can run that once, and then we can use those results to quickly calculate the response for different connection scenarios. In this case, different connection models. All right, so let's open that up, and I'll open it up in BBEdit. So date is just a command that puts the current date in the output file. So that's just a document when the run was made. Hide parameters, is we've seen that before. We're doing this in 5,000 meters of water, so it's going to be deep water. We're going to use double symmetry in this case. Again, double symmetry does add some complexity, but that's what this file does. There are 5 bodies, and now I'm using, I've instead of using the default value for KH, I'm using a value of 4, and you can check that help file here for what that means. It's down here. It's explained down here. So I'm going to not go into that detail. So first of all, let's open up the file to get a schematic of what we're doing here, and it doesn't matter which one of these we use because it's in both files. This, by the way, shows the sketch, or the mesh of the wetted surface of a single module, And this, okay, this is what I wanted to show. So this is the orientation of the modules. Module 1 is the farthest forward in the X1 direction, and Module 5 is at the tail, and Module 3 is at the center. So we need to specify the location of these modules. All right, so I can close this, and that's what we're doing here with the hide coordinate axis command. We have five modules, so we need to have 5 coordinate axis commands, one for each body. So the body 1 is the x coordinate of the body fixed coordinate system is at 600 meters in the inertial coordinate system, and ZB is going to be at minus 12.13. ZCG is the location in the body fixed coordinate system of the CG. So that tells us that the origin of our body fixed coordinate system is at the CG, which means the CG is at minus 12.13 meters. And then body 2 is at 300 meters. Body 3 is 0. Body 4 is at minus 300, and body 5 is at minus 600. All right, so then the next command specifies the wave angles and wave frequencies. In this case, I'm using this option here, the dash frequency. That means the numbers I'm putting in are frequencies in radians per second. So we're going to look at 9 wave angles, 0, 15, 30, 45, 60, 75, 80, 85, 90, and frequencies from 0.1 radians per second out to 1.55 radians per second. Then we're going to read in the mesh. So first we're going to read in the nodal coordinates. And in this model, in this case, I've separated the nodes from the panels in terms of they're in separate files. So we can look at that. So it just gives some information on the slash star asterisk, of course, means it's a comment. So there are 2001 nodal coordinates. Remember, we're only modeling the upper quadrant, the positive, the part of the structure that is in the positive x, positive y coordinates, because we're using double symmetry. So that's 2000 nodes, and that's the end of that file. And then the next file we input are the panels. So let me just open that up as well. So we've got 2020 panels for that 1/4 of the structure. And we're going to look at a mesh in a little bit here once I've run the program. So it'll become a little bit clearer to you what I'm talking about. All right, so to look at the mesh, I'm exporting the graphics, and then we can view the mesh that way. And I'm also going to run hide body check. And then I'm going to have a return here right now just for, so we can run this, stop here, look at the output from these body check commands, and also look at the mesh. So let me start up Hydran, and I need to change the directory. So come to here, and now we want to check, select this guy, and I want to type in the project name here, and we file that in, and we're done. And so if we look at, well, let's look at the mesh first. So let's look at the mesh first. Okay, so you can see here that we're only looking at 1/4 of the mesh. So we just have for this is one of the pontoons for body 1. This is one of the pontoons for body 2, and this is half of one of the pontoons for body 3. So we can see that the mesh, and it looks fine. I can't complain too much about that. Let me just pull this around here. Here, I want to rotate this. You can see that the green is the wetted surface, and here we're looking inside the columns, and so we're seeing this yellow color for the inside of the columns. All right, so that looks fine. So I'm going to close that. And now we can look at the results for the hide body check command. So this is for body 1. And by the way, all of these modules are identical, so these results should be the same for all the modules. So again, X projection, Y projection, Z projection for the volume calculation. They're all very close. You're going to get, because of it's done numerically based on the mesh, you're going to get a little bit of difference, but it should be very small, and we can see that the difference is not significant. The center of buoyancy is calculated here. So for body 1, we know that it's 600 meters forward, so it's a little slightly off, 600.18, very small number. Again, it's going to have some numerical errors associated with the numerical integrations. And this is the Z coordinate of the center of buoyancy. This was input, and this is the difference. And remember, for this body, we're going to want the center of buoyancy and the center of gravity to be on the same vertical line. There's a slight error here associated with the numerical mesh, but it's acceptable. And then for body 2, same thing. We get similar results. And then for body 3, we get the results for body 3. Because we're using double symmetry there, then this comes out to be correct. I mean, there's no numerical error there. All right, so we can now go back and, I'm just going to, well, I'll keep it open and I'll just continue on here. All right, so I've commented out printing the hydrodynamic nodes. Otherwise, it's just going to create a lot of output. And we have hide rigid modes. We have 3 commands now, and we generate the rigid body modes for body 1, 2, and 3. Now remember, these are going to create for each body the 6 rigid body modes: surge, sway, heave, roll, pitch, yaw. And for body 1, we're going to we're saying that it has a symmetry of single symmetry. We're only using single symmetry for body 1. That's what this meant up here, right? Single symmetry. We're using single symmetry for body 1, and it is reflected to create body 5. Similarly, body 2, we're using single symmetry because of where it's cut, where it's located. It's symmetric about the mesh is symmetric about the XZ plane, not about the YZ plane. But it's reflected about the YZ plane to create body 4. And then body 3 is double symmetric. Well, that's specified up here, and it's not reflected. Say, okay, so it creates the rigid body modes for all 5 bodies now, right? It's going to create the rigid body modes for 4 and 5. Modules 4 and 5, even though they're not modeled explicitly. All right, as I mentioned in the previous video on the examples, we have to give the mass matrix for each of the 5 bodies. So we give it for body 1, body 2, 3, 4, 5. Now these bodies are identical, so the mass matrices are all the same, so there's no difference there. All right, so we're using double symmetry, which means we can get away with using 1/4 of the number of panels and about 1/4 the number of nodes. The penalty, if you will, is that it does require a little bit more complexity in setting up the model. So right now we've defined the degrees of freedom, and there are 30 of those, right? 6 per module. There are 6 modules. So we've got surge, sway, heave, roll, pitch, yaw of module 1, the same 6 for module 2, 6 for module 3, module 4, module 5. What we need to do is we need to you take those 30 degrees of freedom, those displacement patterns, if you will, and create 30 displacement patterns that have the symmetry, anti-symmetry conditions that we need to exploit double symmetry. So that's what this transformation matrix psi is all about. So let's look at this one paper here. It's in the International Journal of Offshore and Polar Engineering. It's one of the papers that I highlighted previously. And remember, our module or numbering is 1, 2, 3, 4, 5. And we come down here, and this is where we talk about setting up this alternative definition for the displacement patterns that we're using to define our motion. So U is a 30 by 1 vector, and the first 6 components represent the surge, sway, heave, roll, pitch, yaw of module 1, and then the next 6 represent the surge, sway, heave, roll, pitch, yaw of module 2, and so forth. What we need to do is we need to transform those into degrees of freedom P, which they're called P here, which are going to be symmetric, and we need to define this symmetric, anti-symmetric. So we need to define this psi matrix so that when we multiply psi times P, we get the quote-unquote physical displacements U. All right, so that's what this psi matrix does. And if we come back to, let me just hide that. If we come back to here, it's defined in the separate input file psi.txt. So I've already opened that, and let me make sure I've got it all here. Okay, so remember, so column 1 is going to transform this new mode of motion 1 into displacements corresponding to the surge, sway, heave, roll, pitch, yaw of each individual module. So if we look at it here, it's got a 1 in row 1 and a row in row 26. So that corresponds to surge of module 1 and surge of module 5. So that means module 1 and module 5 are surging, all the other motions are 0. So that's about the XZ plane, that's going to be a symmetric mode of motion, and about the YZ plane, it's an anti-symmetric mode of motion. So that's our new mode of motion 1, and so we need to tell the program that, and we also need to tell it what the symmetry, anti-symmetry characteristics for that mode is. So we use HYDRAN modes for that to do that. So this says that, okay, mode 1 is going to be symmetric about XZ, anti-symmetric about YZ. And then if we go back to psi, the next one is surge of module 1 and negative surge of module 5. And that's going to be symmetric about XZ and symmetric about YZ. And so if we come back to here, we see we've defined mode 2 to be symmetric about both planes. So the next one pretty much does the same thing for sway. Now, sway, this says sway of module 1 and sway of module 5. Now that's going to be, what is that? That's going to be, if we look at here, that's going to be anti-symmetric about xz, right? And symmetric about yz. So anti-symmetric, symmetric. And you can see how we're doing this. So the next one would be positive sway of module 1 and negative sway of module 5. So if we come back here, we see that's going to be anti-symmetric, anti-symmetric. All right, so we have to do that for all 30 degrees of freedom. So once we've done that, the program will deal with the transformations internally. And so we run the HYDRAN analysis command to calculate the added mass, the hydrodynamic damping, and the wave exciting forces for these 5 modules. And again, it doesn't matter. We haven't specified the connections yet because it doesn't matter whether they're connected or not connected in terms of calculating the added mass, hydrodynamic damping, and wave exciting forces. And then I save those results so that I'm going to have the added mass, hydrodynamic damping, and wave exciting forces available for the next step, where we're going to calculate the response of the MOB. All right, so let's do that. Let's run that. So I'm just going to do a new project. I'm just going to run everything from scratch. By the way, I deleted, if you recall, I deleted that return. So we will be running through the whole thing here. Now we have quite a few frequencies here. So I'm going to take a break. But I'm going to show you in real time how long it's taking this. And this then becomes, because it does take a little bit of time, it becomes, that's the motivation for using double symmetry. However, on the other hand, it's not that much time, so you may say, well, you know, I'm going to just bite the bullet. I don't want to deal with a psi matrix and the generalized modes business, and I'm just going to use the 30 degrees of freedom and no symmetry. It'll take longer, requires more memory, but with computational resources in this day and age, it's not that big of a deal. All right, I'm going to take a break here and let this run through, and then we'll be back. All right, it's finished running. It took about 762 seconds of CPU time. Was that about 13 minutes, I guess? And it has saved the results to the database file, so we can use it for additional analyses now. So let's go back to the folder, and we can see what we've got here. So K0000, so that just means this is 5 unconnected modules. So we've already got the 5 unconnected modules, but we didn't calculate the response. So what this file does is it calculates the response of the 5 unconnected modules. So to calculate the transfer functions for the 30, surge, sway, heave, roll, pitch, etc. degrees of freedom, we're going to need to transform the response coordinates, the generalized coordinates that we're calculating when we solve our equation of motion, back to, let's call them physical coordinates. And so we need, and that's what the Hyde mode mat matrix does for us. And in this case, the psi matrix is just the Hyde mode mat matrix. I file in the psi file again here. I don't really need to. It's already in the database. But anyway, that's what I do. And I read the database and calculate the response and then calculate the transfer functions. I will do it just as demonstration. So let's come here. We're going to type in new project, and it's going to be K0000 and file in, and it's done. Like I said, that part is very, very fast. Calculating the response really takes no time at all, because it's only solving a 30 by 30 degree of system of equations. So if we look at it, we of course our transfer functions are here, and we've talked about what these are. These are complex. So for example, LL TF, they're complex. If we wanted to plot the RAOs or obtain the RAOs, we could just take the absolute value of those. And by the way, you can use the up and down arrow to cycle back through previous commands. Didn't mention that before in this series of videos. I've mentioned it before in other videos. Another shortcut is if you can kind of remember what the start of a command is, but can't remember the exact command, you can start typing the letters and do control space, and it will come up with a list of options like that. So for example, let's say we had hyd_p, and I don't remember whether it's parameters or what. You can come up and it'll list the commands that start with hyd_p and so forth. So that's another shortcut that may not be well known. All right, so let me cancel that and come back to the folder. So let's look at these files here. So KBeam models the connectors with beam elements or frame elements, whatever you want to call them. KSpring models the connectors with springs, normal springs. KStiff2n models the connectors using the stiff2n element of HYDRAN-XR, which is just it allows you to specify a stiffness matrix that you can use as an element. And KTruss uses truss elements, one-dimensional in the sense that they just have axial force, axial deformation as their response quantities, but you can orient them in three-dimensional space. So they use truss elements for the stiffness, or to model the connectors. Now, why do I have so many options here? Just to demonstrate that different structural elements can be used to model the connectors. Some are easier than others. Some will do things that others won't do. I'm only going to look at a couple of cases here. But before we do that, let's come back to this article here. And so the modules are connected at the deck level, essentially, with the connectors on each side, port and starboard between the modules. So connector 1 is here between module 1 and module 2, connector 2 between 1 and 2, 3, 4 between 2 and 3, 5, 6 between 3 and 4, and 7, 8 between 4 and 5. They're, again, as I said, they're essentially just connected at the deck level, and they resist translational motion only. So you can imagine that as a spring, X spring, a Y spring, and a Z spring at each of these locations to resist the relative X, Y, and Z displacements between the respective modules. So let us go back to the input file here, and let's look at KSpring, because one might think that this is the easiest way to do it. So we have to define nodes, structural nodes, to use the structural elements. So we need to define 5 nodes at the centroid of each rigid module. The displacements we're calculating are at the centroid of the module, because that's where we specified the body fixed coordinate system. And so node 1 is at the CG of module 1, 2, 3, 4, and 5. Okay, so we have those displacements essentially when we've solved the equations of motion. Because the modules are rigid, the displacements at the deck level are rigidly constrained to those the displacements of the respective module CG. So we'll look at that in a minute. But the rest of the nodes here that I've defined are to define the connectors. So this node 6, for example, is the connector, are between modules 2 and 1 on the port side, and then 2 and 1 on the starboard side, and so forth. I actually define more nodes here than I really need to. This is an old file, and I did it this way, but I actually separate nodes for the X connector, Y connector, and Z connector. Didn't really need to do that, but that's what was done in this file. Here we set up the nodal constraints. So we constrain the nodes that are at the deck level, fore and aft, to the corresponding node at the CG. So this is for module 1, module 2, 3, 4, and 5. So in this in this file here, I'm defining spring elements, and to understand the syntax here, one should go to the help file, and one can type in find help spring, and then you can read what the input is supposed to be like. But no, spring. So this is where we define the connectors, and then we come down here, we form the stiffness, and this is going to be the stiffness associated with so-called physical displacements. In other words, the surge, sway, heave, roll, pitch, yaw of each module, which is not what we need, right? What we need is the stiffness transformed to our generalized modes, which are symmetric, antisymmetric. And so that's basically a double matrix multiplication of psi transpose k psi, and that's what we do here. And then we need to form a modal matrix so that we can extract out the transfer functions or REOs for the connector forces. And so that's what we're doing here. We're determining the connector forces for unit displacements. And then we set up a Hyde mode mat matrix, which involves both which will give us both the motion REOs and the connector force REOs. And then we calculate the response, and we calculate the transfer functions. So that's with the spring element. There's the stiff 2n element, which allows us to define a stiffness matrix. And in this case, since we just have 3, the stiffness is related to the 3 translations, we can define a 6x6 stiffness matrix, and the only values are going to be on the upper 3 diagonals for the X stiffness spring, Y stiffness spring, Z stiffness spring. We still need to define these nodes at the connection points along with the constraints. We need to constrain those to the CG nodes. And then we can assign these or create these elements, if you will, between nodes and using our connector stiffness matrix. And the rest of this is similar, modified for this particular element. But the basic solution is the same. And it's the same for whether we're using truss elements for the connectors, or we're using beam elements for the connector stiffness. Of course, the details necessarily change, but in essence, we're doing the same thing for each. It's just to provide an example of how we can use these different elements to model connectors. I'll finish this up with saying somewhat obvious, I think, if you're watching this video, and that is, when is this model, this rigid module flexible connector model, appropriate? And it's appropriate mostly, the most practical case is when the modules are very stiff relative to the connectors. And that would then mean that most of the deformation is going to be in the connectors, and the modules, the deformation of the modules can be somewhat ignored, at least for the global hydroelastic analysis. If that's not the case, then one would need to do a more sophisticated hydroelastic analysis, such as what we do in the OMA barge case. So coming back to this folder here, the OMA barge uses a structural finite element model for the structure, and is a more general hydroelastic analysis approach. That's discussed in a whole separate series of videos that are posted on the website. Well, this ends the video on the MOBE RMFC example.